Welcome back to the easyJulia Coding by Mathematician channel in YouTube. So today we're going to talk about the Prolate Spheroidal wave functions. We will try to plot them, and we will try also compute and plot the eigenvalues of the Prolate Spheroidal wave functions. So if I go here Prolate Spheroidal wave functions, I will be able to see the first link in Wikipedia. So if I click, I will see this page. So the Prolate Spheroidal wave functions, what we mean is the special version of the much more generalized version. We've got two types of the Prolate Spheroidal wave functions. The radial part, which is coming from the eigenfunctions of this ordinary differential equations, and the second one is angular wave functions. What we mean by Prolate Spheroidal wave functions is the eigenfunctions of this ODE, which is angular wave functions. And in this ODE, if we put m equal 0, then we will have the Prolate Spheroidal wave functions of order 0. But actually, we will refer to the Prolate Spheroidal wave functions 0 order 1. Okay, so the other reference that we can provide is my thesis. In the first chapter, you can see information about the one-dimension Prolate Spheroidal wave functions. And also in my webpage, in this page, if you click on this, you will see a note which I have provided here, and you can start study and understand the Prolate functions. So also there are a couple of other links here that you can see. GitHub one, and the GitHub one is the Julia codes are here. You can visit this webpage and download the corresponding files. Okay, so let's go back here. This is immediate reference for understanding Prolate functions. So the Prolate functions is the eigenfunctions of the LC operator. So LC operator is this one here. Okay, if we put C equals 0, this will be simply differential equation for the Legendre polynomials. So which is given here. Here is the same as this equation, but in this equation, C is equal 0. To be able to compute the eigenfunctions of this operator, by knowing that the Legendre polynomials are bases in L2 space, then we can write the Prolate functions here as the linear combinations of the Legendre polynomials. Now, our mission is to compute the coefficients. Once we have these coefficients, we will multiply them by Legendre polynomials, and we will sum them up to compute the Prolate functions. So you can study these details here. At the end, we will reach to this matrix, three-diagonal, doubly infinitely three-diagonal matrix. We will have to truncate matrix. It means we will have to truncate this summation. Actually, we will approximate the computation of the Prolate functions. But if we choose a big number, it can be a fairly good precision of the Prolate functions. Now, here we've got this matrix. Once we have this matrix, the eigenvectors of that matrix will provide the coefficients for us. Okay, by having the coefficients in this equation here, 3.5, we will have our prolates. So we will be able to compute and plot them as a result. Now let's go to the VS Code. Now you see that the matrix have been created here by this function. It's doubly three-diagonal, so I can have a 0 matrix at first, okay, and then I can start to shape those three diagonals in the matrix by the for loop. Okay, so this formula is coming from this matrix here, m times m minus 1, okay, and it is exactly here, m or I times I minus 1. And you should be careful about I equal 2, and you should be mindful that our matrix is the indices in the Julia is starting from 1, just like MATLAB, unlike Python or SageMath that they start from 0. For example, it affects here in the original diagonal. It is easy to explain the original diagonal. You see that I equal 1. As a result, if I go to the here, you see that m times m plus 1, where m starts from 0. Okay? Therefore, but my m or I starts from 1. So I will have to, instead of m times m plus 1, I have to write I minus 1 times I minus 1 times I, or m minus 1 times m, which is here m minus 1 times m. Okay, so this should be applied to this lower diagonal as well. Okay, actually this one is the upper diagonal, and this one is the lower diagonal. Okay, so we can see that this is the matrix that you see that the first row is here, and the second row here, and the third row is here. So you see that C is equal 1. C is the same as that C in the LC operator, and M is the size of the matrix, 3 by 3. Alright, so the coefficient of this matrix, once we have this matrix, we will have to use the like LinearAlgebra package. Okay, you can remember that how we are able to install the packages in Julia. So now we are going to compute the eigenvalues and eigenvectors. Actually, we don't need the eigenvalues, just eigenvectors. Eigenvectors of the previous matrix. So the function, the way that we define the function is this. Okay, so function, it is depending on the C, that constant parameter. M is the size of the matrix, and N is the showing that which eigenvectors. It's 3 by 3 matrix, or actually here is 5 by 5. So I choose the first eigenvector actually. So once, if I compile the Julia, I will have this one. Okay, by pressing Ctrl L, I was able to clean the terminal of the Julia. So let's try this one again. So this will be the first eigenvector, and the second eigenvector will be this one. All right. We can use the packages to be able to have the Legendre polynomials, but I preferred to practice way of writing the function again in Julia. So I use this reference, okay, numerical analysis with Julia by this author, E13. In page 207, we can use the Bonnet formula for the Legendre polynomials to be able to compute the Legendre polynomials. So we will discuss the packages, something like including special functions later. So we can have this one actually. Okay, I need to compile the function to be able to compute the Prolate functions. Now time to compute the Prolate functions. We see that x is the Prolate functions is defined on the line, so x is showing the line. Okay, c is the parameter, constant c. M is the like showing the shape of the matrix, size of the matrix, or it is the same as the truncation parameter. So how many polynomials, Legendre polynomials we want to use to be able to compute the prolates. So the way that we are defining the function, we need to parameters, that both of them are global parameters. Okay, y equals 0 at first. W is the coefficient, like beta mn, which is coming from this function. And in the loop, we are going to have this summation here. In the loop, we are going to compute this summation. You got this one, so every summation wk times to the Legendre polynomials. Legendre polynomials, this Legendre polynomial is the non-normalized version. To be able to normalize Legendre polynomials, we have to times the Legendre polynomial by the square root of k minus 1 over 2. So k is the order of the Legendre polynomials. Now here is wk, w1, and the first eigenvector. Okay, it has this wk is a vector, and this is an scalar. This is a scalar, and the first Legendre polynomial, it starts from 0. We have first Legendre polynomial is like p0, the second one is p1. So that's why I have put here k minus 1, not k. So if it was like Python, I would write here k equals 0, and I would leave this one like k. Now, by having this one, we will be able to compute the Prolate functions. Okay, so the first one, this is the Prolate functions. Okay, now we can use this is the plot, but we will try to use this one later. So we can use the plot functions here. So the plot of here we are going to use to have the plot to plot the several Prolate Spheroidal wave functions. So the first, so we will choose a truncation 20 summand, or like, I mean, this I will truncate this infinity by 20 or 19 because m starts from 0 ending 19. It means we have 20 summand. Okay, so 20 of them, and I would like to compute the first, second, third, fourth, and fifth Prolate Spheroidal wave functions. Okay, so this one I can plot this one. So now we can have this. The plot is like here. So I have saved this, and you can see the Prolate Spheroidal wave functions here. Okay, let's have just one of them. Okay, so I have to once I have this one, I can have this one as well. So it's again here. So I just need to click on this, and we can have this one. Now, how about just plotting here? So what happens if I plot? So it plots here. So what happens if I just plot this one as well? Okay, both of them. So the first one is this one. It doesn't have 0. The second one, this is the Prolate. The blue one is the Prolate order 0. Okay. And the second one is the Prolate order 1, and it has just only 1 0. And can I have the third one? Should have. This one is 1, 2, like 3, 2 zeros in the Prolate number 3 or Prolate number order 2. Okay, now we are going to compute the eigenvalues of the Prolate Spheroidal wave functions. It is possible to prove that the Prolate Spheroidal wave functions are also the eigenfunctions of this operator. This one is very familiar to most of the mathematicians, finite Fourier transformations. In fact, it is the usual Fourier transformation. Just the difference is like the interval has been truncated. So the interval is finite here. So that's why we call it finite Fourier transformation. And also the range is truncated as well. So the output has defined in the like in the finite interval. So that's why we have put this one as well there. Now, so the proof is here. You can see everything here, and you see that this GC, assuming that phi of t is the Prolate Spheroidal wave functions, we see that it is equal to this guy. So it means this alpha is the eigenvalue. We are attempting to compute this alpha. So the alpha, it's obviously, it's like equal to, if we are able to compute this one divided by the prolate itself. We divide the computation of the eigenvalues into two parts, the even eigenvalues and the odd eigenvalues. The even eigenvalues is corresponding with the order of the prolate functions. So we see that obviously this eigenvalue is equal to this fraction. Okay, so we are able to reduce the calculation of the even eigenvalue to only this part. The denominator here, you see that it's the linear combination of the Legendre, even Legendre polynomials defined only in 0. And this one is like the first coefficient times square root of 2. Okay, so here you see that the linear combination, the denominator has been defined here. Okay, so it's just coefficients. Okay, this part is here, and since the indices not in Julia not starting from 0, it should start from 1. That's why you see here it looks like odd, but in fact it is like the this one is for the even one. Okay, so we've got this one, so we have to compile this one to be able to get result in the eigenvalue, to get the computation of the eigenvalues. The odd part is also here, mu c2m plus 1, and it's like this formula. You can just easily study these files. There might be some typos, but I'm pretty sure that if you study in details, you will be able to understand. So we have to compile this one as well. As a result, the even eigenvalue is just the first coefficient times square root of 2. I just apply this fraction here. All right, this fraction here, and divide it by this denominator. Okay, so which is given here, and I need to compile this one as well. The odd part is also the here. Okay, now the odd part has got one imaginary number I, and therefore I will not, so the odd eigenvalues in the prolate functions, in fact they are purely complex value, so we compute just their absolute value. So we see here that we've got this one. I have to compile it, but in the plotting times I've put like absolute value. Okay, so if I compile this absolute value, I will have this one. So see this one, the first 20 eigenvalues, and the first one is the blue one, is the when the C is equal 1, and the C also is called the constant. C is the same as the constant in the ODE, and C is also called bandwidth because it's also here.